I mentioned, I'll get to your questions here in just a minute, but I mentioned in class how the first multiple choice question will be a little bit different. It's going to be similar to the ones that we've seen. Hey, y'all, make sure I get your names written down before you leave, okay? That it'll be a little bit different. And it's sort of like this. This isn't the question, but it's similar to this, where I ask, what is the force that's acting on the plus Q charge? What is the force acting on the plus Q charge? And it'll be one of those where you have a range of vectors that you can choose from. In this case, those will be pointing up, up and to the left in the quadrant 2. Was that quadrant 2? The way that I do this is, well, let's see. I can first just draw my vector due to the 2q in that direction, and then I'm going to write Coulomb's law. Just help me to think about it. KQQ over R squared. Notice here that I have a charge that is 8 times the 2q charge. I'm going to write that there. What I'm saying is that this charge, the 2q, is 8 times this charge. So just because of the charges, the force that's acting on this should be 8 times the force. So I'm going to write that 8 there, and then I write an 8 over here too. But there's also a difference in the distance, that the 16q charge is 4 times the distance away. So I have 8 over 16. That means that the force due to the 16q charge is half the length of the first vector. Y'all follow me on that? That's a little bit different. It's really not that much different, but it's different a little bit. Yours will be something similar to that, where you just sort of have to think about it in a slightly different way. And then also, I ask you, remember I said I will ask you what is the distance, or excuse me, not what is the distance, but what is the angle for that vector. So the answer for this one would be a vector that would be up and in that direction. And say, for example, if I wanted to know what that angle is, well, the components of that vector include a force that is F, and then F over 2. And then I want to know what is this angle right here. I can still do my inverse tan, where I would just say the inverse tan of opposite, that's F over 2, divided by F. The F's cancel, fortunately, because I don't know them. And so that's the inverse tan of 1/2. That will be the second problem. Okay? First problem is like problems that we've done before, except you're going to have 2 charges that are of some quantity. Right? Just pick one and draw the vector. Just draw any vector. And then write Coulomb's law. And then write down the differences. Here I have 8 times the charge and 4 times the distance. That's 8 over 16 because the distance is squared. So I should have a vector here that's half the length of the first vector. And then I'll ask you the angle. I have a vector in this direction that's F, a direction in this direction, a vector in this direction that's F over 2. And so to find the angle for that vector, I say the inverse tan of the opposite over the adjacent. The F's fall out, and then I can calculate theta. A little bit different, like stuff you're capable of doing, but just a little bit different than what we've seen before. Is that clear, y'all? No? Okay. Why don't you ask me afterwards? Though I do have a concert tonight at 6, so I'm going to have to leave right at 5 down at Central. Are y'all going to the concert too? The honor band concert. My daughter is in the honor band. Y'all going to keep me from seeing my daughter in the honor band? Huh? Yeah, right. Let me step through it again. So these are questions that we've done before, where I have a configuration of charges, and I want to know what is the vector, the force is acting on this charge. I first draw the vector. I'll draw it on this charge due to the 2q. I just draw it any length, doesn't really matter. And then I ask myself, well, how much bigger or smaller is this vector? That's where I write Coulomb's law, K2q over R squared. This charge is 8 times that charge. That's sort of where this problem becomes a little bit different from what we've seen before. It's also 4 times as far away, so that means this vector is 1/2 the original vector that we drew. Okay? And then I can can calculate the angle by doing the opposite over the adjacent. Alrighty? All right. Go. You probably want to go back and look at that question on the video, okay? Is that clear? I went over the first two questions. All right. What do we got? What do you want to do today? You have questions? Particular questions? Yeah, JC? Sure. Number 4. Okay, where can you place a charge, or can you place a charge at one of the positions so that it experiences 0 force? First of all, it doesn't on any of these, it doesn't matter the sign of the charge. If you change the sign of the charge, it doesn't matter. It's just going to flip all the vectors around. It will never matter the sign of the charge. So E is not an answer. And when you're going through the process, just pick a charge. Maybe just always try it with a positive charge. It's always going to be the same. Okay? Is it possible to place a charge at one of the marked locations? You remember what we said is, well, gosh, this is, let's just pick them, okay? So I have, I'm going to go at point A. I'm going to have a force that's big and in that direction, and 2 forces that are small and in that direction. Let's see. No, that's not right. What's the answer? D. Is this it? Shoot, sorry, I messed up. Yeah. No, I don't think that's right. That question's not right. No, it's definitely not C. Because at C, I would have a force in that direction and that direction that would be the same, and then another force that would be towards the negative 4Q. Look, you're not going to have a collection of charges that has 3 charges like that. Is that clear? That's why you're asking it, right? Because it's different from all the others. Yeah. Yeah, you won't see that. Is that okay? Yeah, I don't like that question. All right, what else? Particular questions? Number 3? Yeah, this is like the one that we were doing before. This one's a little bit easier. But on this one, I want to know what vector best represents the force on Q. Again, just pick one and draw a vector. I'll draw a vector, a force vector that's acting on that one. That's going to be an attractive force. And then for this other vector, all right, at Coulomb's law, F equals K Q Q over R squared. I know that there's going to be an attractive force between here and here because it's a positive and a negative charge. It is a charge that is twice as big as this charge, right? 4Q is twice as big as 2Q, and it's a charge that's twice as far away because 2D is twice that of D. So I have a factor of 2 over 4. So this force would be half the length. Actually, this is almost identical to the one that we just did, right? So that force is half the length of the first force. Say what I said, do it again. I draw a vector here. It's attracted towards that negative 2Q. Doesn't really matter the length of that vector. It's just sort of my initial guess. And then I imagine what is the force on this charge due to that charge. I can write Coulomb's law. This has twice the charge of this one. I have a 2 right there. It's twice as far away as this one. So I have a 2 right there. So I have 2 divided by 2 squared. That's 2 over 4, 1/2. And so I drew this vector right here at half the length of the previous vector. Now, to figure out the resultant vector, it's going to be the one that's closer to the big one. So D is the right answer. Okay, Trish? Yeah. You will see some questions like that. Right. Question number 1, in fact. What else? Yeah, Allie? Oh boy. Of course. 5 and 6 on 2016. Okay, 2 electrons and a third charged particle. I'm going to draw a line right here. 2 electrons. I have a negative particle right here and a negative particle right here. And a third charged particle are located at different positions. I don't know where the third particle is. I want to know where the third particle is and what is the charge. So first of all, if I have a negative particle, right here, I have a repulsive force from there and a repulsive force from there. So I can have negative and in between the electrons, but I can also have positive and in between the electrons because it would be attractive in that direction. Huh. Well, that doesn't seem right either, does it? You're digging too far back. So it should be either A or B. Or is that what you were thinking? Yeah, it's either A or B. Both A and B are correct answers. If I have a C negative with both electrons on the same side, that would look like where I have a negative particle over here. But in that case, I would have repulsive forces in that direction. So I can't get a zero force on that. And then D, positive with both electrons on the same side, that would be a positive charge over here. And it would be attractive. So I can't have that with a zero force. So it's either A or B. A and B are both correct. Is that what you thought? Okay. And then 6. I have these 3 cubes, and I want to know what the charges are on them. And I tell you that cube number 3 is positively charged. I know that this one is positive. I know that because the resultant force is in that direction, I know that the 2 component forces are in that direction and that direction, right? Because those 2 vectors make up the resultant force. It's in the middle of them. So if I have a vector here acting on a force here that's acting on this positive charge, that means that this charge has to be positive. And then likewise here, this charge has to be also positive because it's a repulsive force. So I know that cube 1 is positive and cube 2 is positive. So B is the right answer. So again, the way I do this is I know that my resultant vector is there. So the 2 component vectors are on either side of it. Like I can't have vectors that are in this direction in order to get that resultant vector. They have to be on either side of it to get that vector. And the only way to get those are to have right charges on either of those, on both of those. Is that clear? All right, what else, y'all? Okay, on the free response, everybody's good on that? Yeah, Scott?
Can we do number 15 or 25?
25, yes. Okay, so you are going to see a map of equal potential lines like this. You should probably expect that. I'm sure you've seen them on past exams over the last number of years. I have a 3 coulomb charge that's stationed at point A. So my 3 coulomb charge is here. That's at a potential of negative 10 volts. And then it moves into point C, which is at a potential of 30 volts. So I'm going from negative 10 volts to negative 30 volts. That means that my change in potential is equal to 20 volts. Actually, it's going from negative 30. It's actually negative 20 volts. Although the sign is not important because we're just looking for the amount of energy that it gains. Y'all follow what I did there? I'm moving from minus 30, or so from minus 10 to minus 30. That is a change in potential of 20 volts. It's actually negative 20, but this line is not important. And I want to know how much energy does it gain. Remember that delta V is delta PE divided by Q. So if I want to know the energy that it gains, delta PE is just going to be delta V times Q. That's a G, Q. So that's going to be 30 times 3 coulombs, so 90 joules. I don't know that this equation is on your equation sheet. This is our basic definition of what is potential. Potential is energy per charge. It might be on there. Oh, it is. Okay. Scott?
So on the answers, it says that it's A.
A.
It's doing and in the video, because I was confused as well, because I thought it was like a number in your video you get please coulombs.
Oh gosh. Yes. It's 20 actually.
Okay.
I'm sorry. I wrote 30 there. Why y'all fix me? Y'all knew that. He's making a mistake. Is that what y'all are thinking? Yeah. What? Yeah, the change in voltage, I said that actually, is not 30, it's 20. Because I'm going from minus 10 to minus 30. That's a potential change of 20 volts. So yeah, the answer is 60 joules. Sorry. Yeah, Kate. 20? There was a freebie question on this one, by the way. The following graphs potential versus position. You release an electron at point A. What direction will it move? Remember, I always try to remember my mountain. Remember, positive charges move downhill, negative charges move uphill. That's from high to low potential. So if I have an electron at point A, that is this potential. The electron will tend to move uphill. So the electron will move in this direction. There are actually two correct answers for this, where it will either move to the right or it will oscillate around point B. I think the answer that I gave in the key was C, right? It will oscillate. Yeah. You ever imagine that you have a bowl and you have a bead right here and you let the bead drop down the side of the bowl? What it's going to do is it's going to move towards the bottom, and then it's going to go up and come back down, and it's going to oscillate back and forth. You ever done that? Put a bowl in a bead in a bowl, and it goes back and forth and back and forth. The same is going to happen here with our electron. It's going to tend to move in this direction, because when it moves in this direction, the potential increases. Electrons will move in the direction of increasing potential. They move up the mountain. It gets to the top, in this case, which in the bowl analogy, that would be the bottom. It's flipped upside down. And then it would go back and forth. It would go, and then come in this direction, then go back and forth. It'll oscillate, just like a little bead in a bowl that will go back and forth. It's called a potential well. That electron gets trapped inside of that potential well. All right, there will be questions like that. There's not a question like this one, with that kind of graph. I think that's right. Let me double check that. Because students sometimes get confused about it. And then there are two answers to it, as I said. Yeah. Okay. So there are questions that are asked about a change in potential for charges, but there's not a question with a graph like that, with V versus X. There are no V versus X problems. Okay. What else, Al? Scott?
Can you do the short response?
Mm-hmm. All right, this will definitely be on there. So for the first part, for part A, remember, potential is energy over Q, right? Energy per charge. So kinetic energy is equal to Q times delta V. Kinetic energy is 1/2 mv squared. Q delta V. I can solve this now for V, which is 2Q delta V divided by m square root. This is an electron. So an electron has a Q of 1.6 times 10 to the minus 19, and it has a mass of 9.11 times 10 to the minus 31 kilograms. Those are both on your equation sheet. They're in the upper left-hand corner. Oh, God, my nose itchy. Upper left-hand corner, there's a little square that has all those constants in it. You will have the full equation sheet, by the way. It'll be on a separate page. You'll tear it off the back, and you'll kind of hold it right next to you. So this is square root of 2 times 1.6 times 10 to the minus 19. Delta V, I'm going from 2 to -4 volts, so that's a delta V of 6 volts, divided by the mass, which is 9.11 times 10 to the minus 31. All right, whatever that value is, it was some thousands of meters per second, okay? And then for the electric field, I know that the electric field, oh gosh, I forget how this is shown on the equation sheet. It's something like E is delta V over delta X or something like that. E is equal then to delta V, which is 6 volts, divided by delta X, which is 0.2. That's equal to 30 newtons per coulomb. Always remember it. We can express our electric field in volts per meter too, which matches up with this volts over meters. That's how I remember this equation, this relationship. That's it. Okay. Okay.
So 2021, the first response E.
Is there a mistake on it? Is that what you're asking?
No.
All right, 21.
Yeah, E specific.
I mean, I'll show you. It's simple. All right, let me show you because it might come up in the multiple choice. But your free response is going to be like last year's. Like all the questions are the same. It's just a different configuration of charges. I copied and pasted the words, changed the numbers, changed the figure. Is that clear? All right, but this one, once you find the electric field at point A, the electric field would be in that direction, somewhere like over here. That's the electric field roughly, I think. If the electric field is in that direction, whatever the magnitude of the electric field is, if I want to know the force, I just say the force is Q times E. And so whatever the magnitude of this electric field is, I just multiply it times the charge, which is 3. So I just say 3 times the electric field, and then that gives me the force. And then whatever the direction of the electric field is also the direction of the force. But not on your free response. Okay, but it might be in the multiple choice, where I say, here's a charge in an electric field. What is the force that acts upon it? Okay? Yeah, Emily?
Either 18 on 23 or 17 on 22. They similar.
18 on 23. Which one am I on right now? Or what was the one on 22? 17? Okay, yeah. So I want to know where the potential, or what must Q1 be to make the potential equal to 0. Now, first of all, I know that Q1 has to be negative because Q2 is positive, so I can get rid of D and E because it has to be negative because I'm adding two numbers. One is positive, one is negative. For them to equal to 0, they have to be opposite. And then I could just say that, well, V1 has to equal V2. In order for the potential here to be 0, the potential due to that charge has to equal that charge. That has to be equal and opposite, right? So that would be KQ1 over the distance, which is 5, has to equal to KQ2, which is 9, divided by, 3. My K's cancel. That's 3Q1 equals 9 times 5 is 45. So it has to be negative 15. 45 divided by 3. Those come up fairly frequently where I ask you what must this charge be or what must this distance be in order for the electric field or the potential to equal to 0. In those cases, you write out the expression for each of them and set them equal to one another because usually you have two charges. You're not going to have more than two charges. And you determine the potential or the field due to one and set that equal to the potential or field due to the other because they have to cancel one another out. Is that clear? This one's easier because it's a scalar quantity. I don't have to worry about directions. But if it was an electric field, they would be equal and opposite. They would be in opposite direction. You can't do it if they're not collinear. They just don't cancel out. that answer your question?
I just want to know where the KQ over 3 is that from A.
KQ over 3. KQ over 3 is this, this one right here. That's not a Q, that's a 9. It's K times 9 divided by this distance, which is 3 meters. See, there's no base on it. That's Q. That's 9. Okay? All right, what else, y'all?
Why are you using 3 if it's for point A?
Oh, because the distance from here to here is 3 meters. The distance to the 9 magnet coulomb charge, this direction is 3 meters. Okay? Is that all, folks? Yeah, Kate.
Can you do 16?
Of course. Okay, I want these to have the same potential energy. Remember, potential energy equals KQQ over R. If these have a potential energy of, say, 1, well, it doesn't matter. It doesn't matter. If these have a certain potential energy and I move the charges 3 times as far apart, then what must happen to this charge in order for it to have the same potential energy? Well, I triple the distance, so I have to triple this charge. So whereas I have 1 coulomb here, now I have to have 3 coulombs. I have to have triple because I tripled the distance, and it's an inverse linear relationship. I have to triple the charge too. Write your equations on these. That'll really help you. And be careful, because there's electric field, that's KQ over R squared, so there's a different relationship. Always write your equation, and then you can write in what the different variables are doing, and it'll help you to see it better on your page. New students, you can write on the test. I encourage you to write on the test. Like I said, you have an equation sheet, you have your bubble form, make sure you know your N number. You'll have an hour to finish the exam, you have assigned seats, bring a calculator. Anything else I need to tell them? Okay. All right then. That's all? All right, y'all. Y'all have a good day. Make sure if you came in, about 4 or 5 of you came in right at the time, make sure I see you before.